Hi, everybody. I hope everybody can hear me. So a bit of introduction. So as Heidi said, I worked on virtualization at Red Hat, and so QEMU, KVM, the standard Linux virtualization stack. And I strongly believe that that we get the best out of technology by having this strong collaboration between academia and industry. So that's how I am involved in Red Hat research. Without wasting too much time speaking about myself, I will introduce you to Baisakhi Ray, who's an assistant professor at Columbia in the Department of Computer Science. Baisaki's interests lie at the intersection of machine learning and software engineering, which is obviously like a very interesting topic. There's a lot of scope in this area, and of course, it's a very hot topic as well. Let's be honest there. Um, so her work has been widely recognized. She has received the NSF Career Award and as well as IBM and VMware Faculty Awards. She also has many Best Paper awards in her area of work. So today she's going to talk to us about fuzzing and how you can apply machine learning, specifically neural networks to fuzzing. So fuzzing, as you all might know, is basically having these structured, variations in inputs to a program so that you can have a wide coverage of all the code paths that are in that program. And the advantage of doing that is with all these variations in inputs and coverage through the entire program, you have this, you have a greater chance of finding bugs before they are out in the wild, right? So she's going to talk to us about her, ongoing work in this area, and then hopefully we can have some interesting conversations around the topic. So the one thing I would like to mention before I hand it over to her is if you have questions throughout the period of the talk, just write them out in the stage chat, and I'll write them down. And at the end of our presentation, we can go through the questions. And if there's still not enough time left, we can definitely carry over the conversation to the session. So with that, I hand it over to Baisakhi. Welcome.
Thanks, Vandan, and hello, everyone. Thanks for inviting me here. And today I will talk about efficient fuzzing with neural program smoothing. Vandan already gave a very good introduction for me, but this is some of the interesting work that is going on at Columbia University. So before I talk about fuzzing, let me briefly introduce where we stand, what we do, and how this fuzzing work is related to the whole big research project agenda about program analysis with machine learning. As we all know, software is everywhere, right? And what happens when software goes bad and starts producing error? Well, it can cause financial loss, it can have distress, and in the worst case, it can be like even fatal. So even simple bugs can cause big headaches sometimes. You probably have heard about Equifax data breach that happened in 2017. It has a huge identity theft, financial loss. The company lost around $14 million, I believe, in this whole process, including share value drop, and then they lost a lot of client base. So these software bugs are pretty bad for company, for at individual level, everywhere. And what research efforts we are taking to reduce the software bugs? Well, there are lot of tools are developing over decades to reduce this kind of bugs, and as they vary widely from the guarantee these tools provide, right from model checking or static analysis and all the way to fuzzing, which is purely dynamic analysis and which is basically the objective of today's talk. However, before going there, we were wondering, even after this decade-long research and industry effort, why we are seeing these high-profile bugs all the time. And so to understand a little bit more on the bug's nature, we did a large-scale study on the bug distribution in real world. So here we took around more than 700 GitHub projects and analyzed their bug histories. And these projects are usually very important projects like Linux, PHP interpreter, etc. And they are written across 17 languages. So what we found that 36% of the commits that are happening to the master branch are related to bugs. And more surprisingly, an overwhelming majority of these bugs are coming from simple programming errors like incorrect error handling, incorrect API usage, simple typo, copy paste. And this is really disturbing because these are the exact reason all these tools that I introduced were developed, so that they will help developers to minimize such simple, or I mean such program related errors. So there is definitely a gap between research and practice. And what is wrong? So many other researchers, including me, did some empirical kind of studies to understand what is the gap between what is going wrong. And in one sentence, what we understand that developers often incorrectly use or underuse the utilities available to detect bugs. So, for example, Johnson et al. Found that though there are lots of static analysis tools available out there, but developers hardly use them because static analysis tools are notorious for reporting, high false positive. Similarly, as a part of our fuzzing work, we checked that how many test cases, unit test cases developers are writing, even in like highly security critical applications like OpenSSLs. And we found, they are really minimal. Like in OpenSSL, they were like 14, 15-ish at that point of time. It was that study was in 2014. So this was really problematic. Like, of course we cannot blame on the developers. They have more, they have to also develop the real software, but the infrastructure that we are developing is not adequate to support their needs. And what we understand with these studies, the success of adopting these tools depends a lot on human judgment. So, for example, if you want to reduce false positive of static analysis tools, you have to configure the program, the bug rules properly, which is non-trivial. So, definitely the success depends a lot on human judgment, which is not scalable, and it requires a lot of domain expertise. So how can we solve that? And here comes the big research question that my group and many others in Colombia are working on: how to automate more towards better software reliability. So with this, in the past few years, there is a big surge on large scale software data that are available in many ways. Think about GitHub. They have lots and lots of open source repositories, and there are other platforms too. Like if you are interested in bug history, there are like Apache Foundation. They have their bug with Bugzilla, Jira, and there are like a lot of things like app reviews, etc. So what we can do now, we can focus on these big software data that are available, and we can build smart software engineering tools by learning from these patterns. And you can think about this large scale software engineering data as like big code, and now apply or develop new machine learning models to build more smart software engineering tools that will hopefully minimize the human effort that I introduced earlier. So let's see how this bug finding thing or the program analysis are fit in this machine learning driven big code situation. So traditionally, when we think about program analysis, there are three kind of program representation that we think about. One is source code and bytecode. And typically you do static analysis when you treat source or bytecode as it is, like static. And then of course you can execute those code and has execution traces, and you can do dynamic analysis on top of this. And on top of that, there are other program specific metadata like software specification, program configuration, other metadata like bug report, code comments, description, etc., etc. And finally, there is also evolutionary data like how software evolves over time. And you can actually apply machine learning on all these aspect of program or software development. So for example, we build mini static analysis based model, a language model to analyze source code. And now we are also working on binaries. Then we have feed forward network. We develop feed forward network for dynamic analysis, which I will talk in details in a bit. And then there are several others like evolutionary data, configuration, etc., etc. You can also learn from those data as well. So as I said, today I will talk mostly about these dynamic traces in terms of fuzzing, but I would be happy to talk about the other analysis. If you are interested, if you are working on something similar, definitely come and join the session, the discussion session. So, okay. Now I will talk about how to do efficient fuzzing with gradient guided optimization. And this is joint work with me, Professor Suman Jana, and our students and postdocs. So what is fuzzing? As Vandan briefly said, fuzzing is you have a piece of software, say for example, the code you can see on the right-hand side, and then there is a vulnerability at line 6. So to expose those vulnerability, your variable z has to be less than 2. But this is a very specific requirement, and to generate a top level input that will produce variable z's value less than 2 is non-trivial. So this is exactly the problem of fuzzing that people try to solve, that generate some inputs that can expose vulnerabilities lying or bugs lying around the code. And how do you generate inputs? Well, the most simple way can be you can randomly generate inputs. Like you have it's a very famous way of, like, you have a monkey, ask the monkey to type random things, and then it will eventually probably crash the computer, and then some bugs will be exposed. So obviously the random fuzzing is not efficient, though it is very easy. The reason is that the program inputs require some structure, and if you randomly generate inputs, those structures are broken. So one of the way people try to implement fuzzing is with evolutionary fuzzing, like genetic algorithm, you can say. So the basic high level idea is that you have a seed input, then you randomly mutate and try to see whether it is producing or rather which mutated inputs are producing bugs. The inputs that are producing bugs, you are taking them and mutated them further. So though again this is somewhat easy to implement, but this is inefficient because when you are randomly mutating, they usually stuck to long sequence of wasteful mutation which do not produce any bugs. And here we come, like how to make this whole fuzzing process more scalable and adaptive, using gradient guided mutation. So let's take a step back and see what the fuzzing problem is. So you have a program input, and our objective is to find bug. And how will you do that? You will basically generate k inputs from the entire input space, right? So if you write this whole problem in the way I wrote the equation, it becomes a classic optimization problem where fx is my optimized function, right, which will increase the number of bugs that I can generate. And in our case, since fx is discrete, because number of bugs are discrete, it is quite hard to optimize. So this function looks like this. You have an input in x-axis, and with some input, some rare inputs, you can see surge of bugs. And our goal is to find those inputs, which will find those inputs. And in this presentation, those will be x1 and x2. So since this is the space is discrete, people modified slightly the fuzzing definition and says, what about my objective function is increasing edge coverage rather than maximizing number of bugs? Because hope is that if you cover more branches or more edges, then you will see more bugs. So now our optimization goal becomes find x that can maximize total number of edge covered, right? So let's see what happens with this definition with a traditional mutation based fuzzing. So say I start with an input, then I randomly mutate and generate another input too, but I am in no luck because my edge coverage did not increase. And then I randomly generate another input 3, again no luck. Then randomly mutate and generate 4. This time I was lucky, so I slightly increased my edge coverage. But then again, because it is completely unguided, I can generate another input 5, and again my edge coverage goes down. So in this way, as you can see, the evolutionary fuzzing is not guided at all, and it randomly generates input without without direct guidance. So that's why it is not efficient. So what if that, you have a smoother function, as you can see here in this figure, which is a smooth approximation of the edge coverage versus input. And then basically now you can follow these smoother functions to optimize your G, which is the objective function. So let's see what happens here. I start with my same seed input. And now because it is a smoother function, I can leverage gradient guided mutation. So I can ask the gradient which direction I should move. And this time I generate 2 and so on. And finally, I am basically eventually moving to a stage where my edge coverage is maximum. So basically, we implemented this idea where you can think about your program that you are testing as a bunch of control flow graph of program, and then we approximated that control flow graph behavior with this neural network here, where my neural network take a bunch of program inputs as training data or input, and the output is basically edge bitmap. And my goal is that how you can mutate it or change this input byte space so that you can get different edge bitmap, and in total you can increase the edge coverage. So this is based on the observation that real world program inputs have critical parts, and most branches are affected by those critical parts. For example, if you think about a PDF fuzzer PDF parser that you want to parse, the PDF header fields are most critical parts that are has decision making logic, right? So you should focus mostly on those PDF headers, and that is the critical part. And what news does is learn to focus those mutation effort on that critical part, because they will eventually cover more and more branches. So with this, this is some result that we got. As you can see, the red one is news, and we compared news with a lot of state-of-the-art fuzzers, including Google's AFL, which is very, very popular. And as you can see that we achieves on average 3x edge coverage than these baselines. And news also found a lot of different kind of bugs, like out of memory leak, assertion crash, heap overflow, etc. 5 of these bugs actually two of these bugs lead to new CVs. So with this, the key takeaway is that use neural network guided gradients to identify the critical regions of your program inputs. And then if you mutate on those regions, there is a good chance you can discover more bugs. And with this, I would like to wrap up where we lie. Today I talked a little bit about program analysis with machine learning and gave you an example how you can do it with respect to fuzzing. And what is the next step forward towards that? So code has lot of features like type information, structural dependency, dynamic traces, etc. So we need to think about how we can build new models that leverage this kind of data, which is very program specific data. And because these data has similar patterns which are also noisy often, we probabilistic model is a very good approach towards that. So with this, I would like to thank you and take any question.
All right. So thank you very much, Basaki. This is a very interesting talk. So we are almost out of time. We finished just in time for our main stage discussion. So if
Uh-huh.
anybody has questions or anybody wants to discuss this further with Basaki, let's move on to the our session roundtable so we can continue our discussion there. Thank you again, everybody.
Thank you.
Okay, so yeah, while people are joining in, Baisakhi, I think maybe I can start the
Of
discussion.
course.
So one of the things I was thinking of as a developer, and I don't know if Alex is here. So Alex from BU, we have been working on a fuzzing project of our
Mhm.
to fuzz the QEMU virtual device layer. And
Mhm.
what my impression has been is that sometimes the more kind of challenging part of fuzzing anything um, is basically how to realize how do you actually fuzz this new program, right? For example, like QEMU does not have a real main function where you go through a set of structures.
Right, right. Mhm.
So my question is, would you figure out the technique that you are going to use to fuzz your program? How easy or how difficult is it going to be to apply your techniques to that kind of a situation?
So that is actually very interesting question, Vandan. And if you think about it, has two big components, right? One is the program you are fuzzing. So in your case, QMU. And then there is this whole input space that you are that you are passing to the program. Today in this talk, I talked about program fuzzing, modeling the program, but then you can think about modeling the input space as well, right? And of course, their interaction. So one way, actually, we just submitted a paper where we are modeling the input space for REST APIs. So you have these servers, and then there we did not touch the server, but we model the the input space, and generate different new inputs and pass it to the program without modeling. And let the program as it is.
I see.
So the reason is that if you exactly like QMU, if your model is, if your target program is little bit I won't say ill-defined, but it's like a big system, right? In such cases, modeling them would be very difficult because your input space is huge, and you
Right.
don't, and input, not only huge, input space is very structured. So in such cases, input modeling might be a good approach.
Okay, so I think from what I understand, um, it all depends on how I'm able to figure out uh, how I'm gonna so how vast the input space is and how I'll be able to take care of it in a
Right.
way.
Yes. Yeah.
Yeah. Okay. Okay. Yep.
So I just want,
So we have Alex
the
here.
thing is that, when you do in the fast your more fast your input spaces, it is become even more difficult to know the critical region, right? Where you will input, where you will mutate. So in
Got it.
such
Yeah.
cases,
Yeah.
if you use
Definitely.
model, that will kind of help you to identify those critical region. There are some papers on file system fuzzing. You can, and
Okay.
yeah, you can have a look. There they um,
Okay.
fuzz the system calls. And then, as I said, we have a paper. If you are interested, I can, this is under submission, where we fuzz the REST APIs, where, instead of systems call, those are REST APIs and things like that.
Okay. Yeah.
Mhm.
Okay. Thanks. Yeah. So Alex, Sanjay, anybody else? Any other questions?
I have a couple questions.
Sure, of course.
Yeah. I actually at the original Oakland talk for your the fuzzer you presented, so I thought it was pretty exciting work.
Thank you.
Yeah. I have a few questions. I'm working on the project that Bondan brought up. I'm a PhD student at Boston University. I'm working
Mhm.
on the project that Bondan brought up for fuzzing Kimu. So it's a sort of a different problem because we're not trying to build a generic fuzzer. We're trying to build something that works for our specific use case. But
Mhm.
so I had about your work. I had some questions. I think initially you had a picture of a function. So with the steps of coverage. So you had
Right.
um, is that something that you know when you're starting to fuzz the program? Because that seems like something that you'd have to almost
So that's again very good question. You don't know because that's like a mapping between input and edge coverage, right?
right.
And if you know that in advance, then the fuzzing is very simple.
Okay.
Because you know the edge coverage, you basically then find the inputs that maximize that edge coverage. You don't need anything basically,
Right.
right?
So yeah.
So
So
basically, yeah, go ahead.
yeah, no, so basically first you need to do some blind fuzzing. So it's sort of very similar to what AFL does, right? But
Absolutely.
then
So there is a training phase
yeah.
of our case, which
Mhm.
we used AFL, um, which first give us some basic information.
Yeah.
And then you can run news with the AFL seeds,
Yeah.
and then it will get more edge coverage, say with some hour, and then you can retrain the model with again with the edges that news covered. So basically I did not have time to talk about them, but the thing is, if you use news in such active learning setting, like you bootstrap with AFL, then run news for some time, and then again retrain it with newly discovered edges, you get much better edge coverage eventually. I mean, eventually means as the time progresses.
Right. Yeah, that makes sense. So I had another question. Do you just immediately, for example, it seems like your fuzzer is well, and the way that neural networks work, it's pretty tied to like a specific input length. So maybe like 4K
That's
bytes or something, right? Most fuzzers, I think, start off with trying to fuzz a single byte and then eventually adding on some additional bytes. So until maybe they generate a valid PDF header or something, and then they keep
right,
going.
right.
So
So that again, I mean, we obviously had that problem, and we had a fixed length. I think it is four. I mean, I forgot the exact length. I mean, but basically, then whatever the byte we had, and then we padded the rest of the bytes for having the fixed length problem.
got it.
Yeah.
One last thing before I maybe somebody else has questions, but like for example, if the PDF header example that you brought up, so maybe the first part of the PDF header, I mean, it obviously matters a lot because they check the version string or whatnot, but
Mhm.
then a lot of the really interesting code is hidden after the PDF header, right? Where you start off with the drawing commands. And those commands, they have different lengths, right? So you can have something that draws a circle, something that draws a point. So eventually, it seems like for something like a PDF parser, as you keep going into the input, there's so many different valid variations that you can get that it's almost that every single byte can result in a coverage difference.
So actually, okay. If you think about PDF,
Mhm.
there is a big data portion, right, where you have this exact content of the PDF. That is not super. interesting for fuzzing perspective, because that is data, right? I mean, there can be data corruption kind of bugs, but more interesting part is where they are making these decisions, right? Like not only PDF versions, but say like the length of the data, where all these things, and you need to check those in the header, right? But in any case, forget about PDF, right? Even if there is another input format which is like more distributed kind of thing, the advantage of using this neural network guided technique is that with some seeds, it is the model will learn which are the byte locations that are more critical, right? So the model does not care whether it is in the header or tail or middle region, whatever. It only needs some training, and then it can kind of, as a local search, it can search allow across, I mean, around that region to find more critical region.
Yeah, that makes sense. I guess it really depends on your target.
It really depends on your target. So for example, like as I was saying, that we did this REST API fuzzing, and REST API is like, say, GitHub git command, right? That is REST API. Put, and it does not have any header tailor kind of thing. It's like full of command, and there also, like, we eventually found the commands that are more critical in terms of implementation, and you can automatically learn that.
Yeah, that's very interesting. I can't wait to check out that work once it gets published. Yeah.
I think it is an archive already, but yeah, if you guys are interested, just let me know. I'll share it.
Yeah, thanks.
Sure.
All right. Are there any other questions?
Hi, Beshaki. Great talk.
Thank you.
So this is an ill-formed question, because I don't know exactly how one would do this, but is there any gain that one would get by using some kind of reinforcement learning, policy gradient or something, where the example I had in mind is there's a model that takes in a byte sequence and generates the next one to try. Except the problem with this is, as the sequence runs for some fixed time budget, the reward signal again would be either edge coverage, probably edge coverage, and then you get the discounted reward for T steps, and then you update your agent. Is there any value in something like that?
I think, yeah, actually, I mean, I don't know whether they formulated the problem as fuzzing, but people started trying reinforcement learning for testing scenario, where you are basically rewarding the inputs, as you are saying, that goes towards certain region.
I see.
And I think especially if you are doing targeted fuzzing,
Yeah,
where you, or maybe you are trying to go cover more remote branches,
yeah,
those kind of settings, maybe reinforcement learning will be better suitable.
yeah, I see. Yeah, and I mean, at least my experience with RL in completely different settings is it can be very sample inefficient, but I don't know if one can potentially get a gain where there needs to be less data from AFL or some known fuzzer.
Right.
So I see, but that's interesting. It's very interesting.
Yeah, I mean, we have not tried reinforcement learning in this setting yet. I think I saw some paper, at least one paper from Kaushik Sen's group in Berkeley about using reinforcement learning. So, yeah.
I'll check that out. Yeah.
Yeah.
And in general, do you think in the systems world, are there problems where you think something like reinforcement learning would be useful? Like the typical one I would think of is something like scheduling. But of course, when systems people would probably say, well, you need something that's where the latency is very low, practical. But are there certain things which you think are interesting where people should be focusing their efforts?
In particular reinforcement learning
or even in general, any machine learning?
So, one thing, again, and I want to share, I am sharing this because I think this is a very promising area. So right now, this configuration space, think about AWS, right? And there are huge number of configuration space, different clients are coming and then running similar kind of software with different demands. So again there and then we were looking at the NVIDIA kind of forum. There is this new kind of bugs that are coming, which says, hey, my job is running great on this systems configuration, but then when I move to another systems configuration in cloud, it is not running.
I see.
Actually, we also saw the same thing today, right? The practice session ran very well in Safari, but this session did not run well on the Safari. And what is going wrong? And a lot of those kind of bugs are related to configuration problems. And we are using machine learning to narrow down those problems.
I see. And is this something where you would basically collect a lot of label data on which configurations and which workload pairs work?
Right. So we need some labeled data. And then again, you can use in this active learning fashion.
Yeah.
Where as you explore more, you learn more.
Yeah, I see. Because actually, even from a Red Hat perspective, that's interesting, because if there's maybe I'm speaking for a lot of other people, but if there's certain data like that where you think, yes, I want to instrument it in a certain way, on OpenShift, for example, then at least we should be able to do that and expose the configurations, the detailed logs, the workloads, all that stuff. Modulo client sensitivity, I guess.
So in that case, in that space, we are also, exploring causal analysis. So instead of just understanding the correlation, right? This is happening. If you go a bit deeper and try to understand causality, then you can focus your data generation effort also there. Right?
Yeah.
So that is another kind of research we started. We'll see what happens.
And are those some kind of Bayesian hierarchical models or the causal analysis?
Yeah, so that is interesting question. So there are a couple of models. One is on just information retrieval kind of models we used. There is actually a reinforcement learning model as well that worked pretty similarly, at least in our setting, but that setting is we just started. And those are very standard causality model we used so far. Yeah,
no, that's very interesting. Thank you.
Yeah, so I think overall as a system infrastructure, this kind of previously we used to use a lot of heuristics for this kind of system research, right? And basically now all we are doing is learning from those heuristics and then make it more scalable.
Exactly.
Yeah.
Thank you. I don't know if anyone else also has questions. I don't want to monopolize the time.
That was an interesting question, because I had kept that my ending question before we sign off. And so thanks, Sanjay, for asking that. That's a very interesting question. Although I did not understand a lot of it, including causal analysis. I don't know what that is, but I was very interested in understanding how and what you think would be the next kind of, where are you interested to apply machine learning techniques, just like fuzzing? What else are interesting areas of machine learning applications? So, yeah.
So, as I try to sketch the whole area, there are these different kind of software artifacts like source code, binary. Another interesting thing we are doing is using like reverse engineering, where again you have the model which you are training it to do little bit reverse to understand little bit semantic. You have a binary code, right? And you kind of guided the model. Hey, say maybe this syntax means an add operation or something like that, and then the model is learning and then doing the reverse engineering.
So it's like going from maybe an ELF file to source code.
Yes,
Something like that.
Again, that is the final goal. We have
Yeah.
from that.
Is there any related known work in this area?
The reverse engineering, using machine. Yes. So there were some. Again, we recently submitted this paper where say you already know a vulnerability or malware in some architecture, and then if you understand the semantic on a different architecture, then you can basically identify the same malware on, a code that is say compiled in MIPS, and then now you can identify the same vulnerability in a bytecode which is compiled in, say x86, something like that, right? So that there was a paper, a kind of old paper by Donsong, where from Berkeley, her group did the exact same setting where the features were hand coded.
I see.
And because it's basically given the problem is that I know that this kind of code looks suspicious because say it is a known vulnerability pattern, but with different architecture that pattern changes, right? And now if you train the model with those kind of patterns, it can automatically detect those vulnerabilities. That's the kind of thing. So Donsong, and then there are some, actually many others are working in this area. And with this language model specific thing, it looks pretty promising.
So let's see. Okay, we have 5 more minutes. Till one, and I know, Baisakhi, that you have a class at 1:15.
Yes,
So
that's true. Yeah.
if there's no more questions, then maybe we can wrap up 5 minutes early, and
Sure.
that might get you more time.
That would be great.
Yeah. So thank you very much. This was an interesting conversation. I really appreciate your time and talking about your
Yeah,
work.
thanks for inviting me. It was great knowing you guys talking here.
Thank you, Baishakhi.
Thank you.
All right.
Thank you.
Bye.
Very interesting.
Bye.